Hey, what's up, guys? So in this video I want to like finish the classical complexity introduction. So as I say, this is just a PowerPoint that you can take home and you can find some interesting thing in it. If you find you don't understand something, then you can just try to on you can just try to Google it and know the try to understand detail because actually the complexity is like the one semester course, right? We only take like one lecture to review it. Also, previous video that we already finished this MP and BB. So one important classical complexity class is called BBP, which stands for bounded probability polynomial. So you can view this as like because the idea is that quantum computing, the quantum nature has probability, right? So this is so when you measure it, you get some probability outcome. So in order to compare the quantum with the classical one, we need to have the probabilistic version of P, right? So you can view this as the probabilistic version of the classical complexity P, which stands for the or some people write as this. Okay, so this P stands for all the decision problem that can be solved using the classical Turing machine running polynomial time. For the PPP, we need to, since it's probability nature, right? It has probability. So we need to like relax the condition. We say that if X in L, then output yes with high probability. So high probability means greater than 2/3. Okay. And when X is not in L or not true, then this algorithm should say no with probability 2/3. Okay, so one famous conjecture is called de-randomization called BV is equal to P. Okay, and if you want to know, this is the highly non-trivial topic. If you want to know some like intuitive way why this is true, then you can go to find some so-called find some obvious video. There's a professor in the Princeton, I think, which spent lots of time working on it. And if you feel like so difficult, you can first find this Terence Tao's blog. There's a like more into like basically Professor Terence Tao is very good at explaining very difficult thing into like more more easier more easier language. So you can try to read it. Okay. So this is a very you can find a textbook. You can find this topic in textbook that one can show that this 2/3 is just rather arbitrary. You can just replace it by half plus some epsilon, where epsilon is 1 over polynomial, and then you will get the same class. So so this will be the next homework, and I will like post it. Basically just trying to let you learn some concentration inequality in the probability theory. Okay, so since we already defined what universal gate set, right? So remember that in quantum that we have universal gate sets. The exact universal is a single qubit unitary plus C naught. And for the approximately, one can use Hadamard and pi over 8, and also something, right? Let's say C naught. Okay, so since we already and then we proved that if originally your exact sampling your exact circuit using M gate, then by Solovay-Kitaev you only need like log of this kind of gate. Additional gate. So it's basically they are in polynomial range. So once we define it, then once we have this kind of framework, then we can define the probabilistic quantum complexity classes. So this is so-called BQP. Okay, so BQP stand for bounded quantum polynomial time, right? If you forget about everything in this course, I mean, hopefully you remember BQP. Okay, so bounded quantum polynomial consists of language L for which there exists the quantum algorithm AX such that AX runs in polynomial time X. This is the same as BBP. If X in L, AX equals to 1 with high probability. So you can see this is different from classical. This is just say that is the probabilistic version of the quantum probabilistic version of P. If X is not in L, then X should output no with high probability. Okay, so 2/3 is the same as the previous. You can just replace by half by any polynomial, but the proof will require like more sophisticated idea. Okay, so BQP, simply speaking, is the order problem or all decision problems that quantum can solve efficiently. Okay, so notice that in order to say there is a quantum algorithm, right? So in our point of view, this should be viewed as using the quantum circuit. Okay, but the problem is that then this may, right? So by definition, this may depends on the case set. But if this is depend on case set, then this definition is ill-defined, right? Because it didn't tell you the case set. But by previous Solovay-Kitaev, that as I showed that as I mentioned that there's only logarithmic difference. So in terms of polynomial, it's well defined. Because that if you use M, for example, if you use M gate of this single qubit unitary and C naught, then approximately you only need M log M divided by epsilon. So that means that you only it's still polynomial, right? It's still polynomial. So that means that they are the same equal footing. So actually this definition is independent of gate set because you take any two universal gate set, then using the Solovay-Kitaev, you can use one to approximate the other, but only take the extra polynomial factor, at most polynomial factor. Okay, so one famous conjecture, which is the underlying of this quantum computing industry, is to say that there exists the problem that quantum can solve, but classical cannot. Simply speaking, BQP, we hope to, what people hope to show, or at least have evidence that BPP is less than BQP. So BQP is larger than BPP, meaning that there is a problem that quantum can solve efficiently, but classical computing cannot. So conjecture is that BQP is different from BPP. Okay, yeah. So this is why people like, or at least that there are some evidence for it. Okay, so philosophy, as I just explained. So we hope to show that what people trying to hope to show is that BPP is different from BQP. Although in current complexity techniques, there's no way to rigorous prove this, right? But there's evidence, right? So for example, the famous one is the Shor's algorithm, which is integer factoring. We will spend like one or two lecture explain all the details. This is very difficult using some number theory techniques. Shor's algorithm, integer factoring. Another like discrete log, and then many others. So these are a problem that we know if we have quantum computer, we can solve it, but we don't know whether there's a good classical computer to solve it. Right. So the current conjecture for this type of is that NP and BQP there are incompatible, meaning that there's a problem, for example, NP complete problem like K set or 3 set that outside the BB. They should out if NP is different from NP, then it's outside NP. Sorry, it's outside P and different. It's not covered by BQP. Okay, so now some words. If PVP equals to P, that means that classical randomization does not give you extra power. At least it cannot give you exponential speed up. If BQP is different from PVP, there is a problem that quantum can solve in polynomial time, but classical cannot. Okay, so there are some history about this quantum complexity. I collected. Okay, so this is just some timeline that if you remember this timeline would be good. Okay, so quantum computing is defined like first by Feynman or something, some like Deutsch or some previous like very in high energy theory, for example, like Feynman, and but this is just from 80s, right? There's no precise definition of the quantum circuit like this, like our language nowadays. But in 1993, there's a Vazirani in UC Berkeley, I think, they define complexity class BQP. So BQP is first defined in 90s. Oh, but then there's a lot of famous algorithm happen, like Simon's algorithm, and the most famous one is this Peter Shor, 1994, using the so-called quantum Fourier transform. So we will explain in detail. Strongly suggests that BQP is different from B under some basically you can do the large factor in the integer. And 1996 has so-called Guaver's algorithm. So these are chapter 5, these are chapter 6 in the textbook. And these two, I would say that is most important quantum algorithm in the 20th century. I mean, Rani and Peter Shaw. And like modern after we are now in the 21st century, right? So now, so people try to develop understand more theoretical part of this BQP. So one is called BQP versus so-called polynomial hierarchy. And after that, people try to doing the quantum computation, really do the quantum computation. So it is a new there comes a new idea called fault tolerance and quantum error corrections. And also another is the quantum supremacy, which is like if you cannot build the full quantum computing, can you like still demonstrate some problem which quantum can easily solve, but classical cannot. This is called supremacy. Okay, and this is the the reason. These are all reason like 10 years. Okay. And so yeah, so we finished the definition of this complexity. So now I still have some time. So I collect some classical complexity terminology, and I'll try to go through it. Maybe it's very difficult or weird to you guys, but you can take this PowerPoint, you can take home and then try to understand by yourself. Okay, so as I say that I want to define NP, right? So NP is a problem. There is a short certificates or verifier or witness or the proof, which you can easily if the answer is yes, somebody just give you that, then you can easily verify it. For example, whether given a graph, right? Is if I give you a graph and then whether this graph is three colorable is in NP because somebody can just give you the color and say this graph, this node is this vertex is color in red, that vertex is color in blue, then you can check whether it's violates the edge condition. So co-NP, you can give you co-NP or the I should say the complement of NP. Basically, it's the problem that if the answer is no, then the witness will tell you no. So if you got witness, then you can just get for all x in L. But if the answer is yes, there's no witness. All right. So for example, I give you a formula, ask whether there's no such x to satisfy this formula. If this formula is polynomial computable, then this is in co-NP by definition. Okay, so this is just the logically you can view is basically the complement of NP. Okay, so to one can use the one notation to understand this NP and co-NP, right? So sometimes that what people write NP using the exist P. So this is borrowed from the calculus, right? This is called exist. This is called for all. Okay. So some people write NP equals exist P. So exist P is basically if the answer is yes, there exists and it exists a verifier. Okay, so this is exist. Yeah, I can write co-NP equals to for all P. So this is for all. Right, so for all, right, this is basically this condition. Okay, because you can do the complement, then you get this condition, right? So or sometimes that people can write NP equals to exist P and slash and for all P. So this is yes case. So yes case means that there exists. And the no case means for all, right? And one can just write co-NP equals to for all P slash exist P. So right? So this is show notation, right? So this for all P, basically that for if X does not belongs L, then there exists. So this is, yeah. Okay. So, yeah, okay. So then one can define a so-called polynomial hierarchy. So you can view NP. NP is a problem that defined using one quantifier, either exist for or for all. And the column B is the same, right? Either using for all or exist. So polynomial hierarchy is the extension of NP, right? So NP definition is that there exists dot 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 dot, dot, right? For yes case and for no case, there's for all, right? So so I can rephrasing a definition in NP in a symbolic way. Right, so I can say L in NP, if there is some polynomial time computable C, such that if X in L, there exists, right? There exists the answer, such that you get that. Well, once you get this W, then you can find the answer. Okay, so column P is the same, right? Now I can define a complexity class. It's called the polynomial hierarchy by what if we have both quantifiers. For instance, we can define a complexity class, so sigma 2. As a set of languages for where exists some polynomial computable function C such that when X in L, there exists for all U such that for exists U for all W such that CX U W is 1. So this is you use two quantifier. So that means that if the answer is yes, then there exists the U, and for all W such that some easy computable function is true. Okay, maybe this looks like very difficult. Okay. And there is this is called sigma 2p, which contains both NP and co-NP. And to see why this is true, you just neglect one quantifier, right? You can just neglect one quantifier. And one can also define a complement called pi2. You can view pi2 is the complement of sigma 2. It's like you exchange for all and exist. So for all U, there exists the W such that is 1. Okay, so maybe it looks very weird, but I want to provide one example that such that you get a feeling. And the non-trivial result is that sigma 2 and pi 2 they are both contains the randomized class called BVP. This theorem that you can try to find out the proof. This is very interesting proof. It's a cool proof. Okay, so let me explain. Let me give you one example such that maybe after this example you will find that the definition is not so weird. This is called I copy from Wikipedia, but I think this example is very pretty standard. This is called sigma 2. This is so-called minimal circuit, right? So you know that circuit theory that one thing people like to ask is that, oh, I give you a circuit, can you provide another can you like try to minimize the circuit, right? Can you like find another circuit which output the same, which has the same functionality but use less gate, right? This is somehow in the circuit theory or electronics. But how do you write it in terms of logic, right? So how do you write it in terms of logic? Okay, so one way to do is that we collect set such that called a KBX. This is not important. Such that so you can view A and B are two circuits, right? Two circuits. So L is a set of B has at most K gates and A input X is the same as B input X. So you can view this as I give you a circuit A, and I want to ask whether you can build another circuit called B such that B use at most K gates and A of X equal to B of X for some particular inputs. Okay, so now I can define another language called CM where input is A and K such that there exists a circuit B with at most K gates such that A and B computes the same function. Right, so now I require for all X. Okay, so if you read this sentence, it says that there exists a circuit B, right? At most K gates such that computes the same function, meaning that for all X, you compute the same function. So that means that what minimal circuit is asking is basically this, right? You try to find a circuit. You try to ask where there exists a circuit. And for all inputs, it computes the same. Right? So if you write in terms of logic, it says that for exist and for all, right? So this is the very nature in electronics, right? So that means that, so this is why they give you the intuition you need to build such complexity classes. Okay. And so now if you believe this is true, right? Maybe conceptually you believe, oh, this is minimal circuit, so uh that you feel like, oh, maybe it's not so weird, then we can define it, keep going, right? You can have the three quantifier or four quantifiers. Okay. So this is the guy, this is the thing called polynomial hierarchy. So simply speaking, one can view sigma 2 is basically exist for all, right? And the pi 2 is for all exist. And the NP is exist, co-NP is for all. Then you can define sigma 3 to be for all exist for all, right? Exist for all exist. And the pi 3 is for all exist for all. So basically it says that, so notice that we always using existent for alternative, because if there are two exist, you can combine with one exist. If there are for all of two quantifier, you can combine, right? So you can define a sigma 3 by, yeah, you can define sigma 3 by adding an extra start with the exist and define a pi complexity class starting with for all. And then you collect all of it, right? You collect all of this sigma I and the pi I and collect all of it, and they become a tower. And all the union of this tower is called the polynomial hierarchy, which is a very large class. Okay, polynomial hierarchy. Maybe you see a picture. So, by the way, this is our copy from Wiki. So this P is the classical complex deterministic polynomial time, and the NP is the non-deterministic polynomial time. And the composite of NP, then you can define more. You can define the whole tower. Okay, so one famous conjecture which is extended from P, right? So the famous conjecture of is that P is different from NP, but this polynomial hierarchy conjecture is claiming that all of them are different, right? You pick any two of them, they are different. The tower is infinite. Tower is infinite, and this has some very difficult. Never there will be, if you believe this is true, then you can show that there is a problem that quantum can solve and classical cannot. And then this is the very deep results. And if you so I would like to bring some like connection or like analog in real analysis. If you learn some like advanced analysis or learn some topology, you know that in topology there is an idea called open set and a closed set, right? Closed set is defined to be the complement of open set. So so in topology, one say, oh, I define something called open set, right? And then one can define as closed set by define closed set as a complement of open set. So I can say G is a set of open set, F is a set of closed set, right? And I can define a so-called G delta, which stands for intersection of open set, and F sigma to be union of closed set. So, and one can keep going. I can define G delta sigma, which is a union of intersection of open set, and the F sigma delta basically is the intersection of union of closed set. So one can just keep define hierarchy. And in the mathematics, it's like people spend like many years just trying to find out where these sets are actually the same or not. And the answer is that they are all different. Now you can prove basically deep mathematical results. So one can view this as a whole tower. You can add it in, so you can view the intersection and the union as for all exist, and you combine, you get similar idea in the polynomial hierarchy. Okay, so this is just for fun. So P is usually, so this is, as I said, there's a shorthand notation. This is yes and no. So for P, if yes case, there's a polynomial time algorithm for no-linear polynomial algorithm. For NP, if yes, basically there's show proof, then if the answer is no, then for all is you cannot find it an output 0. So co-NP is for all exist, and sigma 2 you can write as this. So usually I write as the left-hand side, and for no case, you just do the complement. And BBP says that high probability, right? So if the answer is yes, then output yes with high probability. If the answer is no, you output no with high probability. So there's a weird notation using this. This is meaning that for most. So yeah, so it's high probability. So BBP, one can view BBP as if the answer is yes, then for most the random inputs, the most random seeds in the algorithm, and if the answer is no, then for most random seeds. Then so once you have this exist for all and for most, then you can use this to combine to define more weird complexity class. So one famous one is called Merlin-Arthur, which looks very weird. Okay, so Merlin-Arthur defines exist for all. Okay, so this is weird. So it says that if the answer is yes, then there exists a short certificate such that for most of the random seeds, you get one. So one can view Merlin-Arthur is the probabilistic version of MP. Right? Because for MP, you say that if I give you a witness, you have 100% to get the answer. But this Merlin says that if Merlin-Arthur class is basically say that if the answer is yes, then for most of the input, you get the answer. So this is called AM and Merlin-Arthur. So so Merlin-Arthur. So this is the interest. This is the funny thing. You can just Google online and find it. It's basically interesting. And one is called the Merlin-Arthur. One is called another is called Arthur Merlin. There are different classes. So Merlin-Arthur basically say that if there's a input, if I give there's a witness, if I give you the witness, then your probabilistic computer will output a answer with high probability. And Arthur Merlin is different. Arthur Merlin say that it's basically okay. So Arthur Merlin say that us you so one can view this scenario as you are the author, right? So you are the author, but only have probabilistic Turing machine or the standard computer, and then there is an infinitely powerful guy called Merlin, some very powerful magician. He will give you the answer, give you the witness. So the Merlin author stands for the class which if you're author, but if there is an infinitely powerful guy called Merlin, you can interact with Merlin with one round, and you get the answer. And Arthur Merlin is different from so Merlin Arthur situation is that Merlin give you the certificate Z, and the Arthur run is polynomial computer, right? So run is BBP power, run is Turing machine and output the answer. And for the Arthur Merlin, basically Arthur will first send a coin or send random seeds. Once he sends random seed to Merlin, then Merlin will output his answer to Arthur, and Arthur do the computation. So it's different, right? So yeah, and one can define like more complex, more rounds. You can define a complexity class called MAM or AMA. So MAM basically is Merlin give you Arthur, and Arthur give some random seed to Merlin, and Merlin give the Arthur. Right. So it's basically keep going. Yeah, and if you want to see why this is interesting, you can go to Google find these YouTube videos. I think it's very enlightening. Oh, so these are just some funny things that I will not talk about, but I put this is called Toda theorem. It says that define upper bound of polynomial hierarchy. Okay. And finally, we say about this complexity class, right? PMP or keep going. So the complexity class, what we have seen is the polynomial is keep going, right? You get a very, very large polynomial hierarchy. But there's a complexity class which is very gigantic called RE. So RE stands for recursive enumerable languages. So it says that if there is a Turing machine where we'll enumerate all valid string of the languages. So the definition goes as this. Let me just try to. It says that if X in L, there exists a Turing machine that decides L, but no matter what time it is. So it's like the Turing machine. If the answer is yes, the Turing machine will keep running until and yeah. ultimately will output yes. Right? So for example, I'll give you a program, ask whether this program on this input will terminate. If it terminates, then that program must terminate for some at some time, right? So given an algorithm and input X, decide whether this algorithm will terminate on input X is in RE by definition. And then we define a so-called core RE. So R is very large. R is larger than whatever class we talk about because it's basically say that, yeah, you basically say that if the answer is yes, then Turing machine will output yes. This is the condition. And the famous holding problem given a code A and input X, decide whether AX holds or not. If it holds, then output yes, otherwise output no. Holds is in RE by definition. Okay? Because if B is a Turing machine, so B is just take Turing machine, simulate A and input X. If AX indeed holds, then you will hold some tiny B can decide. So, and the non-trivial proof is that the non-trivial result is that holding this whole problem is RE complete. Yeah, so this is our complexity class. So this is for the classical case that we suspect because we cannot prove almost everything rigorously in the complexity class in using this unconditional this unconditional complexity point of view. And so the problem in quantum computing is whether how this BQP fit. So these are all people suspect. So we don't have the rigorous proof, but this is what people believe. And if you want to find some more interesting complexity, you can go to find the website called Complexity Zoo. And there are more than 500 complexity classes. There are people think they are important in very different cases, like communication or other kind of thing. And there are more and more complexity classes that people define right now. But most of us know like one or up to 20. Okay, so go to complexity zoo, there are different animals out there. Okay, so the big question in complexity theory is that there are different complexity classes, or some of them can be equal. So there are few famous results, like IV equals to P space. I will not tell you what this means, but you can find it online. And the famous ones, and another is MIP equals to NX. And then there are total theorem, PH polynomial hierarchy, a subset of Peter sharp P, and the post BQP equals PP. And the 2020, there's a breakthrough called MIP star equals RE. You can just Google it and find what this terminology mean. But basically, why these are big results is because they prove that two complexity classes are the same. You can define a complexity class as before, but to prove there are two of them looks quite different are the same are highly non-trivial. Just for fun. Okay, so the rest, of course, to give you some evidence and why and very short for a guy like evidence for what like vector is not become leader are very interesting in your content can solve it and give you some evidence that why people believe that BQP is different from PVP. Yeah, okay. So foundational complexity is like two semantic forms, like very difficult. You can not very, but it's very fun. And hopefully this PowerPoint will inspire you. Okay, thanks.